So our final speaker of today is Ruoyu Sun from UIUC, speaking about dealing with constraints via random permutation.
Thanks, Ben. Thanks to the organizer for the amazing workshop. I'm glad to be here to talk about the recent journey into this random permutation. Something that is very strange. We have a very little understanding from, maybe the whole math field. But it turns out to be interesting for constraint optimization. This is joint work with Tom Law and Inyu at Stanford. This is mostly a theoretical work, but I will show some simulation results to cross the line of Ben. Again, interesting simulation results. So the big question I want to answer, or try to understand, is how to solve large-scale constraint problems. Well, people are talking about large-scale optimization for a long time, but mostly we're only solving unconstrained problems. Traditionally, convex program is about constraint optimization. The interpretive methods have been very successful, but how can we apply that idea, existing ideas, to constraint problems? Let me briefly review the popular idea of solving unconstrained problems. Mostly, one popular idea is to solve the small subproblems one by one. And that's not only good for time, but also for memory. When you have a big problem you cannot store in one single machine, you may want to get single coordinate or single data one at a time. Now, this has been successfully applied to coordinate descent and SGD. It's widely used in practice, including deep learning, and Mark mentioned some applications in Lasso and SVM. Current packages are using coordinate descent. And also for matrix completion, you can also apply these ideas. Okay, so still, Stephen Wright has a nice survey about this. He said, well, this idea is so simple that optimization people don't care too much in the past. Nowadays, still, we have a lot of competitive ideas. Why do we care? Well, I would argue that it is, compared to other ideas, it is very has some similar idea as using cheap iteration, but it's also orthogonal to other ideas. For example, first-order methods use gradient information for the computation, but it can be combined with coordinate descent or SGD kind of ideas. And Mark showed some examples. You can use coordinate idea, but using second-order update. So it's independent idea of first-order methods. I think understanding this will help with other orthogonal lines of research. And another example is sketching. You can do sketch, but then use this idea again. Now, linear constraint problems or general constraint problems are pretty common in practice. Traditionally, it's used in combinatorial optimization, which is the theme of this workshop, and also in operations research problems and statistical problems. There are many machine learning applications, include structure sparsity, that you can solve you cannot solve easily by traditional proximal gradient methods. Now, can we apply the same decomposition idea? It turns out to be quite tricky. And I will show you some, you will see that in maybe half an hour. But to start with, we cannot simply apply coordinate descent to solve the problem because there is a constraint. And we need to consider a Lagrangian multiplier and use ADMM to solve it. That's one way to solve it. Okay, that's the general framework of ADMM. You have a general objective function, and you have linear constraints. And you form an augmented Lagrangian function. And for the primal problem, you optimize over x size. And for dual problems, you do a dual ascent update. But it turns out this algorithm doesn't work in general. For 2-block case, it was known to converge for a long time. But 3-block case, it may diverge. A simple example is given in recent paper showing that even for solving linear systems, it doesn't work. Okay, it seems that maybe that's just a bad idea that we shouldn't pursue. But interestingly, we found that if you randomly permute this update order, it works. This is a simulation for that counterexample. The Cyc-ADMM diverge always, and the random permutation makes it converge. And the question is why? And is there anything interesting there? Okay, this is the outline of the talk. We have talked about motivation, and I'll give some background on ADMM and the general why do I come up with this idea, and discuss convergence analysis. For people who have attended my talk before, I will give some new stuff maybe in the last 20 minutes or so. Some interesting new findings. And then in the end, I will talk about convergence rate analysis, which is a very tricky theoretical problem, and we have some recent progress on that. Okay, this is the traditional ADMM, popularized by the survey of Stephen Boyd and a few people, including Eckstein. It got 5,800 citations, surprisingly. The first time I gave this talk is about 2,000 citations. Well, for mathematicians, we shouldn't care too much about citations, but still, is quite interesting. So they care about the problem of objective function is sum of two parts, and you have constraints about the two blocks of variables. And you apply ADMM, but just for the two blocks. Okay? And when f and g are convex, this is known to converge. Multi-block case, it may diverge, but the question is how to make it converge. It has been an active topic of research in the past few years. You could change the algorithm or change the algorithm plus the problem together. There are a lot of works on this. But we're asking a different question. Can we have a minimal modification with step size 1? And it's so simple that every engineer can understand and use it. Now we know at least two things. One, ADMM can diverge, and randomization can help current descent SGD, which was shown is one of the main themes of large-scale optimization in the past maybe 5-10 years, starting from Stromer and Nesterov's influential paper on randomized current descent. The first idea is just to randomize ADMM. So instead of cyclic order, 1, 2, 3, 1, 2, 3, we randomly pick the order, say 1, 3, 2, 3, 1, 2, and so on. The bad news is it can diverge. And what's more strange is it diverges for Gaussian data. Gaussian data is usually the easiest data you can imagine, but it turns out it diverges for that. It converges for the counterexample given there. Okay. The second idea is use random permutation. The difference is in the independent randomized version, you may have x3, x1, x1, so x1 may repeat twice. But in random permutation, it won't repeat any coordinate. And we have shown that it always diverges in the simulation. Quick summary, these are 3 updated rules, and random permutation is the only one that works in practice. Well, some people may say, well, any practitioner may not care. Well, if it works for practical problems, then fine. I don't care whether it diverges or not for worst case example. Okay? But it turns out the divergence is pretty common. Okay? Although that paper only gave an example, we found it can diverge with probability 1 for very common data. Okay, this is simulation result. For Gaussian data, you can see that divergence ratio for cyclic ADMM is only 3%. Very small percentage. Maybe it doesn't matter. If you change the distribution to uniform 0-1 data, or the simplest MATLAB command you can have, it may diverge with probability 1 when you have a large number of blocks. So you don't even need to construct a counterexample. There are so many counterexamples there. It's actually more common phenomenon. If your covariance of the variables are large, then this would diverge with high probability. It's not something about uniform or Gaussian. It's more about the matrix itself, whether it has large off-diagonal entries. This is somewhat similar to cyclic coordinate descent. We observe the same phenomenon, that it works not so well when you have large off-diagonal entries. Okay. So we claim that the divergence of Cyc-ADMM is a robust claim. It's not like worst-case analysis of simplex method. Okay, when you perturb the problem, simplex method will work in polynomial time, or randomized version will work. But here is not worst-case example. It happens quite often. Step size tuning doesn't help really, at least for constant step size. Strong convexity does not help if you have step size 1. Another trick is maybe one order fails. How about if you choose a random order then fix? It turns out for this counterexample, it always fails. So any fixed order diverges. So it's not about a bad ordering. It's actually any order doesn't work. So why do we care about this? It's mostly theoretical curiosity. This is something that we cannot understand. We have no clue why this happened. And there's also a practical need. So as I mentioned, we want to apply this decomposition idea to solve large-scale problems. We don't have too many ideas that works for large-scale problems. Still, people are using, say, interior point methods. But when you have huge problems, how are you going to deal with that? Cyclic version doesn't work, so we have to use some more robust version, which is random permuted version. Second, understanding this may help understand other problems, like random permuted coordinate descent or random permuted SGD. Actually, many people write papers using randomization, but when running experiments, using random permutation always better. Byproduct has a paper on jellyfish, and he discussed the benefit of using random permutation. Actually, it's faster and even saves the sampling time. And I think a lot of people do that when running simulation. Okay. So we'll discuss the simple linear system first, show how to analyze convergence. It turns out to be pretty complicated even for the simple case. This is a basic constraint problem. Many people have issues with why do we analyze this? But most people have no problem with analyzing quadratic problems for unconstrained problem. I would argue that for constrained problem, a linear system like this is as fundamental as quadratic problems. They're essentially similar and equivalent to each other under some transformation. And it's already difficult to analyze, as we will see. The theorem we're going to prove is the expected output converges to the solution of the problem. We only prove expected convergence. It's not the true convergence, but it's a strong evidence for convergence. And the key result is that if we denote the expected iteration matrix as a matrix M, then we will prove that spectral radius of the matrix is less than 1. And notice that for each fixed order, the spectral radius is greater than 1. But when you permute them and take expectation, it becomes smaller than 1. So why do we use spectral analysis? I think this is really getting to a very high-level question. What kind of proof method do we have for optimization? Most people use potential function idea. And that's the one I've seen the most. Like gradient descent or coordinate descent or RCD, they can all be analyzed using the potential function, which is the objective function, objective value. For our system, if you write the expected update, it turns out the spectral norm, which is the largest singular value, is 2.3, while the largest eigenvalue is less than 1. So we cannot use spectral norm to analyze that. Or put it another way, y transpose my is not a potential function anymore. And there's an interesting result from control theory. that if the spectral radius of matrix M is less than 1, then you can always find a potential function, pointed out to me by Farid. There exists a matrix M so that this is PSD, and this is potential function. But the issue is it's very difficult to compute this P. I don't know how to compute it. There is a closed form expression, but it's infinite sum, which is impossible to compute. Another.
Just solve a system of equations.
What?
Why can't you? I mean, you just solve all the up and out function.
Yeah, use PSD to find a matrix at P to make this PS positive semi-definite.
M has its eigenvalues less than 1, or no?
Yes. M is, we don't know yet. We want to prove its eigenvalue is less than 1. Yeah, if you know, then it's easy. But if we can find a simple form of P, then after similar transformation, yeah, you have self-spectral norm problem. Another common method is the contraction for ADMM. By Eckstein has a paper on that. It's a very nice mathematical framework, but the issue is how to distinguish between cyclic version and the random permuted version. Okay. There is a relation between this problem and a switch linear system in control, I recently realized. So we're having linear system, but the matrix, the update matrix M will change at each iteration. So for RP-ADMM, this number of matrices is n factorial, all possible permutation matrices. But our problem is for every single matrix, it is not stable. But using some rule, it will become stable. This field is mostly talking about always stable, and actually it's related. Diverges has a paper about wavelets, this related wavelets, or is called joint spectral radius. But we're talking about more subtle problem that every single state, every single matrix state is not stable, but you want to find some way to make it stable. It's also related to product of random matrices dating back to 50 years ago. But that field doesn't provide too many tools for me. It's too hard to apply. Okay. So the theorem 2 is mainly is a pure linear algebra problem. We have a matrix like A transpose A matrix, and you want to get half of the entries. You form a matrix L, and you take the inverse of L, and then take expectation. Now we want to argue some properties of this Q. That's essentially the problem. And the theorem claims that spectral radius of M is less than 1, where M is a function of A and Q. It's a bit complicated, and well, it can be simplified further, but that's the original form. It turns out the spectral radius of M is related to spectral radius of AQA transpose, which is a symmetric matrix. Less than 1 is equivalent to a spectral radius, or not spectral radius, but the eigenvalues lying in this region. So what is that matrix AQA transpose? It turns out to be related to the update matrix of a coordinate descent. And we'll prove second lemma that this is really the case. And 4/3 should be tight because we find examples greater than 1.33. So this is really the tight estimate. So what's the relation between this and the random permuted coordinate descent? If you look at the update matrix of random permuted coordinate descent is I minus QA A transpose A. So we know RPCD converges using theory of like Bertzikis or Paul Tang. That means the eigenvalue is between 0 and 2. But what we need here is between 0 and 4/3. And as a comparison, cycling coordinate descent, the eigenvalue is between 0 and, well, it's not really between 0 and 2. They are complex numbers. That's actually wrong. Is the eigenvalue is I minus this between -1 and 1. So what's the message coming out of this? The spectrum of RPCD is nicer than cyclic city. That's what random permutation does. It's so nice that it even for not only originally is distributed in this circle inside the disk. Now it forces it to be in a line segment. The line segment is between 0 and 4/3, or yeah, so it shrinks by about 1/3, or 1/3 of it. So it seems to be a pre-assigned space for RP-ADMM, okay? Because this result is about coordinate descent, has nothing to do with ADMM, but there is some pre-assigned space to make RP-ADMM works. I don't know whether that's coincidence or not. The proof is the proof sketch is this. We'll do a symmetrization to get an induction formula, and then using and we write down the matrix expressions to show that the eigenvalues have this relation. It's a bit complicated proof, but it turns out it works. What is 4/3? 4/3 turns out to be the fixed point of this equation. If you make this equality, make rho hat equals rho, then it's 4/3. Okay. I would like to discuss some new findings recently. There are other variants of ADMM. One variant is motivated by the proof. We found that you don't need to use full randomization. In fact, in the proof, we use 3-level symmetrization, but 2-level is enough. That motivates an algorithm called Bernoulli randomization rule, which is a bit strange. I don't think any practitioners would think of this. But if you have the proof, this is very reasonable. We have 2 phases. In the phase 1, we sweep from 1 to n, and we throw a coin for each coordinate. If it is up, then we update. If no, we keep it. And in phase 2, we come back and update all remaining coordinates. That may be too abstract. One example is you have 4 coordinates. You can do 2, 3, and then going back, do 4 and 1. That's one valid order. Non-examples or not valid order is something like if you have 4, 3, and 4 in the first phase, and the second phase, you should do 2 and 1. But if you do 1 and 2, that's not a valid example. So there is some difference between this randomization and the full random permutation. And it's easier to implement. You only need a binary randomization generator instead of sampling from n coordinates. Okay, if you want to save on this random base generator. And we can show that this also converges in expectation. Pretty much the same proof. But go ahead.
Sorry. So, and you can see that from the expected transition matrix, like why such a thing is valid,
right.
Why not valid.
Right.
Just the spectral radius of the expected transition matrix.
I'm not sure I get your question.
So with the Bernoulli randomization scheme,
yes.
you form the expected transition matrix, and you look at the row, and that's less than 1, and based on that, you tell us that's a valid thing to do. But then if you go ahead and do a scheme that allows for 3, 4, 1, 2, the row will be larger than 1?
No, they're both less than 1. But it's just this is a simpler randomization rule.
Sure.
So both work.
What is your criteria for that tells that this would work? Like this is a good.
We have a proof for that.
I'm asking about the sketch of that proof. But anyway.
Schedule of the proof.
Yeah. I can ask this.
Okay, maybe we should discuss offline. Okay. There's another way to apply decomposition idea, which is pretty popular. I think Mengdi may give a talk related to this. The original ADMM is do x1, x2, x3, and lambda. And when we permute the primal update, primal coordinates. But there's a primal dual version where you mix the primal update and dual update, x1 lambda, x2 lambda, x3 lambda. This is different from original ADMM, so I haven't thought about in the beginning. And the cyclic version still diverge. for the counterexample. So I think, well, there's no way to try that. But interesting, it turns out randomized version or independent randomized version was proven to converge for this rule. Okay. So it seems that we have a different algorithm that works, and the proof is quite simple if you have independent randomization. However, I tried a simulation. It turns out to be much slower than other versions, and I will show this in next page. So in short, there is another way to apply decomposition idea, and that will apply a whole lot of new algorithms. And I tried a lot of experiments, but this is one of them. If you have uniform 0-1 data, we know that cyclic ADMM will diverge. That's the figure of a cyclic ADMM. It will diverge. We have a Bernoulli version of that for this primal dual version. It turns out to be diverge for this case as well. But random permutation for this variant works. So the two green lines are the two random permuted versions. One for the original ADMM, one for the primal dual version. Both work, and both are the fastest. Well, one may be faster than the other. The red line here is the randomized version. It's proven to converge, but it's very slow, maybe 10 times slower. Okay. You may say, well, this is for uniform data, but it turns out for Gaussian data, the gap is even larger. This is the Gaussian data. It turns out the primal dual version of randomized ADMM the gap is maybe even larger. I don't know, 100 times or 50 times slower. All other methods, even cyclic ADMM converges for Gaussian data. That's why I say Gaussian data is so nice that cyclic ADMM works, and Bernoulli version works. There are 6 methods here. 5 of them work. But the randomized version doesn't work. Well, it's not work. It's but slow. It's much slower than all 5 other versions. I have no idea why, although theoretically it might be the best. I summarized the comparison. So there are different update orders for either the original version and the primal dual version. Okay, cyclic is the worst, that it can diverge for uniform data. And independent randomization works for one case, but very slow, but diverge for the other case. Bernoulli randomization works for one case, but diverge for the other case. Random permutation is the only randomized rule I know that converge fast for both rules. So it seems that random permutation is a universal stabilizer. Well, if you view this as a switch linear system, it always stabilizes. The gap is even larger than coordinate descent. I've done experiments for coordinate descent. The gap may be 2 times faster, or maybe 3 times. This can be 10 or 20 times faster compared to others. There's one open question I recently realized. Do we have any convergence analysis for the primal dual version of that? Well, it turns out to be not easy. Okay, let me talk a little bit about the convergence rate. So this is more tricky than the convergence, actually. The status is most of the results we have seen is about independent randomized rules. If you want to get very tight analysis, randomized rule is the best bet. We have little understanding of whatever rule besides that. No matter cyclic or random permutation or so-called double sweep, you can imagine there's so many rules. There's some few works by Ben and Stephen Wright. They study random permutation, but I think in general why it is better is still an open question. The classical literature says, I don't care the different rules. Like Paul Tseng has a paper saying all update rules are essentially cyclic rule. Essentially cyclic is as long as you touch every coordinate in finite time, that's fine. It will converge for coordinate descent. However, the convergence speed can be quite different, as we will see. We see that in practice, but also there are theoretical results about that. So my first question is, can we understand the simplest rule, which is cyclic rule? That's maybe the oldest method in applied math, one of the oldest methods, Gauss-Seidel method. It's still in textbook of any linear algebra course. Well, and another reason is related to random permutation rule. Almost all cyclic results can be applied to random permutation. So if we have a convergence rate of cyclic, you immediately get the same rate for random permutation. The reason is when we analyze that, we don't care the cross iterations. We just do one cycle. So that's it. And another reason, randomization not available sometimes, I think. In practice, you will see that. The one puzzle, this has been a puzzle for me quite a few years, that the known rates can be sometimes n squared times worse than randomized coordinate descent. This was initiated by Beck about a few years ago, and we improved it a little bit, but still there's a large gap. Many people claim cyclic order can be bad, or must be bad. They say we know that. One example given by Stromer and Richtarg independently after we posting the paper is you have multiple lines you want to do projection. There's some geometric understanding of that, but it turns out there's only ON gap between these two methods, not ON square gap. Another subtlety is it only fails for one particular order, or maybe some particular orders. If you randomly pick an order and fix, then it works. So, and we want to answer this question, and we showed recently that there's really a big gap up to ON squared times between these two. And this analysis is based on a lower bound analysis. This example was proposed by Stephen Wright in a few talks in 2015, but I didn't know the examples. And we independently discovered the example and analyzed that. This is the simple table. I want to make everything simple. So I don't want to give you 10 parameters. I don't have any explanation about it. To keep it simple, solving quadratic problem, square quadratic problem, and we view the gradient descent takes time 1. Okay, is 1 unit, which is 1 unit is actually n squared times kappa. Kappa is condition number, and the log 1 over epsilon. It turns out there's a nice gap. The randomized coordinate descent has 1 over tau rate. Tau, what is tau? Tau is a key parameter in large-scale optimization, although for a few people talk about it. Is the maximum eigenvalue over the average eigenvalue. Is between 1 and n. Is related to so-called demo condition number. Well, Demo is a professor at Berkeley in linear algebra. Okay, randomized coordinate descent and also SVRG. I don't know whether people compare that. I did calculation. The SVRG or Saga, which are the accelerated versions of SGD, they have the same rate as randomized coordinate descent for the quadratic problem. They're both 1 over tau. So if you think and you believe that SVRG or SGD is faster than gradient descent, you have to admit tau is a big factor that you cannot ignore. It turns out cyclic coordinate descent has convergence rate which is tau, almost tau. There is some extra tau times extra factor of log square n and so on because of more subtle issues. But roughly speaking, cyclic coordinate descent is tau times slower than gradient descent. Randomized is tau times faster. So the gap between cyclic and randomized is tau square. Worst case, n square. Okay, that's the message. The analysis turns out to be quite tricky. I think I'm touched some dark zone of linear algebra. That spectral radius does not provide lower bound for the convergence rate. Because in linear algebra, people talk about spectral radius, that's the convergence rate. But that's just upper bound. Go ahead.
I'm confused. So it gets faster when the condition number is bad? Like 1 over tau? It sounds unreasonable.
1 over tau is unreasonable? It's independent of a condition number. That's extra parameter.
Okay.
So it's actually getting better when you have a non-separable problem. So tau will be equals n if it is totally non-separable, like sum x. Maybe I can write it here. Tau equals n when fx equals sum xi square. And the matrix is all one matrix. And tau will equals 1 if fx equals sum I xi square. Now A equals identity matrix in this case. And for random matrix, tau could be in the order of root n, actually. Okay, relation to other methods. Since Gauss-Seidel is almost the equivalent to Kazma's method, and Kazma's method is a special case of Pox. Pox is projection onto convex sets. The same gap, O(n) squared gap, exists for these methods. I want to say a few words about Pox. Pox, dating back to von Neumann in maybe 80 years ago, is a very popular method in applied math. There is a nice survey about this 20 years ago, including some optimizer like Adrian Lewis. There are some books published like a few years ago called Alternating Projection Methods. The whole book is about this method. The convergence rate was given a classical rate by Smith and a few people in about 40 years ago. That's still in textbook a few years ago. Now, if we translate this result to coordinate descent, it actually will get a rate dependent on all eigenvalues. So the original method is about angles between different subspaces or different sets. But it can translate to eigenvalues based on a very nice analysis there's an inequality about this relation. It turns out this rate, the classical rate of Pox, nobody knows how tight they are. There are a bunch of papers on this convergence rate claim, oh, this is not tight, but then there is a further improvement, but that's not tight as well. It turns out that rate can be infinite times worse than our bound for that counterexample. And we can prove it's always worse than our bound up to some log n factor. Okay, go ahead.
Where's the randomization in these methods? Is Kashmar's randomized and Pox?
Oh, sorry, I'm talking about cyclic version here.
Okay, they're both cyclic.
Yes.
Kashmar's and Pox.
Right. Okay. Randomized is pretty good. Yeah, as I said, motivation is to understand the random permutation, but cyclic seems to be related to that. So I want to mention another thing, why the convergence rate is difficult. It was studied by Ben a few years ago. They mentioned a conjecture called AMGM inequality. So what is AMGM scalar version of this is that you have some ixi to the power of n. You normalize that is greater than the inner product for all xi greater than 0. Now, if you want to generalize the matrix case, it becomes 1 over n sum I ai to the power of n greater than, but then you don't have a product because it's non-commutative. So you have sum over all permutations. Then you have x sigma 1 to x sigma n. Then normalize that. No, not x, but a. So their conjecture is when you have spectral norm, then this holds. I think this is still open. If this inequality holds, then you will have a convergence rate of RPCD for quadratic problem. So that's why I think this is almost the equivalent. If you want to prove a convergence rate, you almost prove this inequality in some sense. We propose another variant of that, which is related to our result. So we replace this general AI by a projection matrix, but we remove this spectral norm. We want to prove this PSD inequality always holds. So there's some benefit to that because you don't have spectral norm. And this is not enough. if we don't have our previous result. So if this holds, but combining with our previous result, the eigenvalue is between 0 and 4/3, then we can prove a convergence rate of RPCD. And the reason is our result, so recall the eigenvalues of the update matrix between -1 and 1, then it converge. Okay. We remove one side. We improve -1 to -1/3. So you don't need to worry about that side. That will only give you a constant rate. Matrix AMGM inequality will deal with the other side. How close is to this one side. And we have some results on that, but still working on that. Okay, the summary, we talk about convergence analysis of RP-ADMM. This can be a solver for constrained problems. So we want to really understand it. But another implication is why random permutation is better. And it's even much better than independent randomized rule for the constrained problems. In probability theory, in math, there are not too many tools about this random permutation. And in linear algebra or spectral theorem, not too many tools about spectral radius. So this is a really difficult problem. Another thing is the convergence rate analysis. The tight analysis of a non-independent rule. We have some understanding, but many more works are needed. There are lots of open questions, including the convergence of p-divergence, AMGM inequality. There's one thing I don't mention, Jacobi preconditioning. Maybe preconditioner is widely used in linear algebra, but even for the simplest case of Jacobi preconditioning, which you have a matrix with non-equal diagonals, then you normalize it, make it equal diagonal. That procedure, does it improve the condition number, was not known, to my surprise. And that's related to complexity of cyclic coordinate descent for non-equal diagonal case. That's still open. Okay, that's all. Thank you.
Questions? So in the comparison between the different variants of ADMM, have you compared with the symmetric Gauss-Seidel update of the version of the ADMM?
Oh, I have not. Yeah, maybe I should.
Because that one is known to be convergent.
Right, right.
So basically you update 1, 2, 3, then 2, 1.
Right, right.
So
Right.
That's guaranteed to be convergent.
Right, right, right. But
you
yeah.
compare it and see how fast it goes.
Right.
compared to
But one reason I think I have this paper is I think for deterministic update rule, there might be a gap between this and randomized rule in the worst case. Yeah, that's one reason.
I'm curious to know what is the gap. Yeah.
Right, right. Okay, thanks for the question.
Would the Bernoulli randomization have any advantages with respect to data access or communication or anything
I
like
think data access can be easier.
that? Yeah.
That when you sample, you can put the data there. You don't need to move around. You just add a label to that. And it go through one loop and come back another loop. Yeah, I think that's easier in terms of data access.